All right, here are the solutions for Section 8, Topic 2, Comparing Linear, Quadratic, and Exponential Functions, Part 2. Determine whether each table represents a linear, quadratic, or exponential function and justify your answer. Write the correct function name and justification next to the corresponding table. All right, so when we look at a table, the first thing we ought to do when we're looking for any kind of patterns is look at your input values, the x values, and make sure that you're not skipping over anything here. This will be a very clear pattern because you can see this is going up by 1 again, up by 1 again. So this is a nice one because we'll be able to see a pattern fairly easily. All right, so let's go over to the y's then. And we'll look at what's going on here. Obviously, this looks like we're going down. So what happens here to get from 5 to 0? We are subtracting 5. And then from 0 to -3 is dropping 3. From -3 to -4, we're dropping 1 more. But then we go from -4 to -3, and that's coming back up again. So there's not really a very clear pattern going on here. So we're going to go one step farther and see if there's a pattern in the second grouping. So from -5 to -3, that's going up 2. From -3 to -1, that is going up 2. And from -1 to +1, that's going up 2. This, if you have the same sum or difference going on in your pattern in the second column here, the second time you look, this is a sign that you have a quadratic function. And that is our justification right there. All right, look at the second table. Again, look at your inputs just to be sure they're not trying to trick you here. So notice this, from 2 to 5 is going up 3. We've skipped over some numbers here. So we're gonna have to keep an eye on that. From 5 to 6 is going up 1. From 6 to 8 is going up 2, and from 8 to 10 is going up 2. So we've skipped some numbers in all of this. So let's look at what's going on here. From 5 to 14 is going up 9. From 14 to 17 is going up 3. Then we're going up 6, and again we're going up 6. So if we filled in the missing numbers here, like from 3 and 4, that would be in here in between our 2 and 5, we would probably see a pattern showing up that would be a lot more recognizable. For example, from 8 to 10, if we filled in our 9, what number would go here in between 23 and 29? It would be 26. And what would we be moving up by? Would be up by 3 each time. So every time we're moving up just a single input value, we're moving up 3. And we can look at this another way. We can say, okay, what would the slope be if this were a linear function? It would be 9 divided by 3, which is 3. And 3 divided by 1, which is 3. And 6 divided by 2, which is 3. And 6 divided by 2, which is 3. Meaning if we had all of these numbers filled in, all the ones we skipped over, everything over here would be add 3, add 3, add 3, add 3. This is definitely a linear function. It has a constant rate of change going on there. They were just trying to trick you by not showing you all the numbers. All right, let's look at the third one here. So let's check our x's again. This is definitely going up 1, up 1, up 1, up 1. So we should be able to see some kind of a pattern going on here. So let's see, are we going down 4, down 4, down 4, like if this were a linear function? No, that's not happening here. This is going down 4, down 2, down 1. I bet there's something else going on, especially because we've already used quadratic and linear. What's our other function? Is exponential, which means maybe we've got a common ratio going on here. We're actually dividing by 2, dividing by 2, dividing by 2. But remember, when we talk about common ratios, we always want it to be multiplying. So we are multiplying by a half. Times a half again would put us at 2. Half of 2 is 1. Half of 1 is a half. So yes, we have a common ratio going on. That's an exponential function. All right, let's go over to the next page. Identify whether the following real-world examples should be modeled by linear, quadratic, or exponential function. All right, each ink cartridge purchased for a printer costs $12. So for 1, we're going to pay 12, and for 2, we're going to pay 24, and for 3, we're going to pay another 12, and 4, we're going to pay another 12, which is a constant rate of change. Our price is constantly going up each time by $12. That's linear. Throwing a ball. Okay, I think this is what they're getting at here. Up and back down. We did a lot of word problems where we had a flight of a ball or a rocket. Those were all quadratic. The amount of money you earn when you get paid an hourly wage. Well, again, it's like this ink cartridge thing. You're getting paid the same amount every hour, and that's growing at a constant rate of change. That's linear. A bank account balance earning an annual interest rate. Well, interest rates, percentages, they are multiplied times your account balance. So that is a common ratio, and what you have going on here is this. That is an exponential function. Maximizing the area of a rectangular fenced area in a large field. I'm going to come right back to that one. We're going to skip it just for a second because I have something to show you. Population growth of a city is just like our bank account. It's going to get faster and faster. So this is an exponential function. Let's go back to this. Maximizing the area of a rectangular fenced area in a large field. Okay, so I did a what if, and I said, what if we had 12 feet of fence? 12 feet. I could use 1 foot lengths on my fenced in area, and then I'd have 5 feet of fencing for these two sides. All together, this would make my 12 feet of fencing, and this would give me an area of 5 square feet. 5 times 1, 5 square feet. Move that over to 2 now. Let's say we use 2 feet on this side. Now we'd have 4 and 4 on the other sides to make my 12 feet of fencing, and you can see that the area of this rectangle is 2 times 4, which is 8 square feet. So let's move that up to 3 feet on a side. Now we'll have, look at this, a perfect square, 3 on each side to make my 12 feet of fencing, which gives me an area of 9 square feet. So my area inside, even though I'm using the same amount of fencing, the area inside is growing. So let's move that up to 4 feet. Now we just have the same type of rectangle here, 4 on this side, 2 on that side, for an area of 8 square feet. And we're back to the long skinny one, that's 5 square feet. So what happened as this side got longer, 1, 2, 3, 4, 5, is the area contained in here grew, but then went back down again. So you can see that the best rectangle you could have for the most square feet inside the fencing would be a nice perfect square. So I graphed this for you. I'll show it right now. With that side length being 1, we had an area of 5, and moving it up to 2, we have an area of 8, then it becomes an area of 9, back down to 8, back down to 5 again. And you recognize this shape, that is definitely a quadratic function. So for this one right here, we are going to select quadratic. There you go. Complete the following table so that f of x represents a linear function. Okay, we need this one to be linear, and g of x represents an exponential function. Okay, so the difference between linear and exponential is that linear has a common difference, you're adding or subtracting something, and exponential has a common ratio, you're multiplying or dividing by something. So let's go to linear. We have to add something. Oh, sorry, our inputs, they're all going up just by 1, so we're good. So what are we adding to get from here to here to here? So find the number that is smack dab between 6 and 14, and you will see that that would be 10. So what are we doing? We're adding 4 each time, adding 4. Adding 4 means we're going to end up with 18. Adding 4 means we're going to end up with 22. All right, that would be our linear function. Now look at your exponential function. What are we doing to get from 1/9 to 1/3? That is multiplying by 3. 3 times 1/9 is 3/9, which is a third. Multiply by 3 again, and we're going to get 1. Multiply by 3 again, and we're going to get 3. Multiply by 3 again, and we're going to get 9. So we've completed this to be a linear function with a common difference. And this one exponential with a common ratio. All right, turn the page. Determine the function whose domain are all real numbers. Choose all that apply. All right, so for linear, quadratic, and exponential, which ones have a domain that are all real numbers, meaning your x values could be anything. So remember when we did domain and range, we did the blue foldable activity. This is domain. This is my domain, the x-axis. Which ones can exist anywhere along the x-axis? So let's look at these. Here's our linear function. Looks like it's going on forever in both directions. So there we go, that's one. How about our quadratic functions? Can they go on forever in both directions? Yes, that is a domain of all real numbers. And exponential functions, here's one. Can it go on forever in both directions? Absolutely. So they all have domains that are all real numbers. Determine the function or functions whose graph has a vertex. So do you remember what a vertex is? That's that maximum or minimum point where you are traveling upwards, but then you turn and come down, or you are going downwards and you turn and come up. So let's look at that linear function again. Does this ever change directions? Nope. Does the quadratic function? Yeah, there's the vertex right there. That's our turning point. So yeah, this one has a vertex. Does the exponential function? No, it's moving upwards at a different rate. It looks like almost a half of a quadratic. It's not, but it's definitely not changing directions. It's not turning and going back up again. So that one's not going to be either. So we have just one answer there. What is the maximum number of times that a quadratic function, I think it's always good to have a picture. So always draw yourself a picture when they ask you about a certain type of function. So what is the maximum number of times that this can intersect the x-axis? All right, here's our x-axis. We've talked about this many times. What is the most it can do to cross the x-axis? Here we go. Twice. Once, twice. Remember, we can have that not hit the x-axis at all, or touch down and hit just once, but the most it can do is twice. What type of symmetry can the graph of a quadratic function have? Can it have symmetry about the x-axis? All right, okay, again, we're looking at this quadratic function here. So let's look at our x-axis. Here it is. Can this shape be symmetrical around your x-axis? Like, for example, this. Is that symmetric on that line? Will it fold over it and match up? Absolutely not. So that is not going to be it. Symmetry about the y-axis. All right, let's look. How about that? Is the y-axis a line of symmetry? Can you fold that right over on itself and make it match up? Absolutely. Symmetry about the line y equals x. Well, the y equals x line is this. Cuts those two axes completely right there, smack down the middle. Does this shape have that as a line of symmetry? In other words, could you fold your parabola on that line and have it match up on itself? And that answer is no. Or does it simply have no symmetry? But we've already seen that, yes, our quadratics, they do have a line of symmetry. It's a vertical line, and the only one of these choices that was a vertical line was the y-axis right here. All right, there you go. Those are your answers for 8.2.